Okay, good morning, lads and ladies. Welcome back to Calc 2. Let me close the door here and we can get started. So lately we've been talking about sequences. We've spent all week talking about sequences, and today we're going to wrap up that conversation on sequences, and I'm going to try to plant a seed of an idea in your brain for the thing that we're moving to next week. Oh, let me and we can get moving. On the topic of your exams, I know that we are all anxious to get them. I've graded some, but not all of your classes' tests. I know that this has taken a little bit longer than I originally told you it would. And the truth is I just haven't had a whole lot of spare time to get in and wrap them up. But they're getting there. I think I'm in the Fs now, so we're getting there with your class. It did work out that of my 4 classes, you guys were the ones that got to the grading last. So next time I'll reverse the order and you guys will get them first. So this is MAC 2312.004. The date today is the, what is the date today? 18th. And what we're doing today is we're going to finish section 11.1 on sequences and introduce section 11.2 on series. When it comes to the stuff in 11.1 that I want to focus on today, there's a few sort of new topics, things we have not really discussed yet. I suppose really just one new topic that we haven't discussed yet. And then there's a couple things that I want to practice that are related to topics we have discussed earlier. So the other thing I want to do is kind of give you a summary or a recap of all the theorems from 11.1 that I need you to know as we move out of 11.1 and into 11.2. So the place I'm going to begin here is with recursive sequences. I don't believe we've really talked properly about recursive, at least how to take limits of recursive sequences just yet. So just one moment here. All right. So a recursive sequence and is one given by kind of two things, a recurrence relation and a set of what are called initial conditions or initial values. These are very similar to, in Calc 1, and some Calc 1 teachers do this with the formal language and some do not, very similar to what are called initial value problems, where you're told the derivative of a function and you're told the function's value at the 0 or at 1. Like I give you a formula for f primed and I tell you f of 0 is 2 or f of 1 is 5, something like that. And then from those, you're meant to construct in Calc 1 the original function f by integrating the derivative and then using the initial value to solve for the constant c. Those were also sometimes discussed, again, depending on your Calc 1 class, as a direction field where that derivative tells you kind of the slope of the function at any given x value, but it doesn't tell you where that slope is vertically. And then you can kind of draw in a curve that matches those slopes and goes through that point that they specify in the initial condition. When it comes to sequences, the goal is a little bit different. certainly it would be nice if we could recover a formula for the nth term of the sequence from the recurrence relation and the initial value. That would be akin to solving the Calc 1 problem. But here, the recurrence relation is not telling you like the derivative, it's doing something else. This tells you how to get the next term as a combination of the previous terms. So it's a rule that tells you, okay, if you have like the first term or the first two terms, the first three terms, how do you get the next one? So if you have the first three terms, how do you get the fourth term? And so on. And the initial values, these are what they sound like. This is just like the first few terms. E.g. A0, maybe A0 and A1. The first couple terms. Maybe the first three terms, but finite number of terms. Our goal with these is severalfold. First, I just want to get you to a place where you can write down, like if I give you the recurrence relation and the first term, get you to a place where you can write down the first 5 terms, first 10 terms. And that way you could sketch a graph of the sequence, you could guess as to the limit, all of that. These also provide a means of defining the factorial, and I think I showed you guys that last time, right? We went through the factorial as a recursive sequence last time. Is that correct? Reversible? Oh no, the word is recursive. R-E-C-U-R-S-I-V-E. Sorry, and this is me not drawing it. R-E-C-U-R-S-I. Recurrence. No, yeah, this is recursive. This is R-E-C-U-R-R-E-N-C-E, recurrence relation. I did see that email. Yeah, I saw a couple emails. Sorry, these are DMs coming to me. I saw a couple emails yesterday. I think I replied to the first one or first two, but we do need, in order to give scores for those problems, we do need to recover those bits of the written work. I'll take a look. If you've sent me emails since then, I'll take a look. I have not been able to go through my email yet today. Okay, so really quick. The factorial as a recursive sequence. Did we get to talk about that last time? The exclamation point sequence? No, okay, right. Very good. So I'm not going to start with that one. That one's kind of a weird example. So I want to start with a simpler example of a recursive sequence. And we'll point out what the recurrence relation is and what we can do with that. We'll point out the initial values and we'll list a few terms and make a guess at the limit. So for example, a nice simple recursive sequence. I can define the sequence an running from 0 to infinity by the rule that an plus 1 is 1/2 of an plus 6. And this is for n greater than or equal to 0. And the fact that a0 is equal to 2. The task here is going to just be to list the first 5 terms and guess at the limit. So I want to try to say whether this sequence is convergent or divergent. If it's convergent, I'd like to have a guess at what the limit is. This piece right here is the recurrence relation. This is the rule that tells you how to get the next term from the previous term. See, if an is a term of the sequence, then an plus 1 is the next term of the sequence, right? Like if n is 3, then this would say a4 is 1/2 of a3 plus 6. So to get a4, you would take a3, presumably you already have that as a number, add 6 to that number, then multiply that by 1/2. So it's a rule for telling you how to get the next term out of the last term. And this would be what's called a first order recurrence relation, because you only need to know the term immediately before to get the next term. But it could involve other past terms like an minus 1, an minus 2, and so on. The piece over here, I say a0 is equal to 2, that's the initial value. And those two things define the sequence. What's missing here, of course, is a formula for an. There isn't one, or at least I haven't been given one. And for many recursive sequences, it can be very hard to find a formula for the nth term, which makes this part, getting the limit, quite challenging, because how do we find the limit of a sequence? Well, we write limit and then the definition of the sequence, right, which is usually a formula for the nth term, and apply all of our tricks and theorems. Okay. They've told us to list the first 5 terms. So let's try to do that. We know that the n equals 0 term, a0 is 2. That's my initial value here. And then if I take this recurrence relation and plug 0 in for n, then I get a1, right? Plugging in 0 for n, this becomes a sub 0 plus 1. And always think of the subscript here as in like parentheses. So plugging in n equals 0, this gives me a1, and this would be 1/2 times a0 plus 6. Again, this piece came from the initial value that was given to me. And the line below comes from plugging n equals 0 into the recurrence relation. What you notice here is that the only piece I don't know right away is a0, but that's the initial value that they gave me. So this has to be 1/2 times a0 is 2 plus 6, which is 1/2 times 8, which is 4. If I do that same thing, but I plug n equals 1 into this recurrence relation, then on the left-hand side, I'll have a sub 1 plus 1, which is a sub 2, is equal to 1/2 times plugging n equals 1, so this is a sub 1 plus 6. And you see the bitch of the thing is that I couldn't possibly figure out a2 unless I had already figured out a1, because in order to get a2, I need to know a1. And that's what recursion is, right? It's where the next thing comes from the previous things. And in some settings, it's really nice. In some settings, it's a big, hairy pain in the ass. A1, we just calculated, was 4. So this is 1/2 times 4 plus 6. 4 plus 6 is 10. 1/2 times 10 is 5. Questions so far? I know it can feel a little strange plugging n equals 0 in here to get a1, and plugging n equals 1 in here to get a2. The number you have to plug in for n in order to get a specific term out kind of depends on this guy. It depends on how the recurrence relation is set up, specifically what the subscript is for the guy on the left. But if you think about it, it makes sense. Okay. Let's plug in plus 2n. I take my recurrence relation here and I plug in 2 for n, then this will be a sub 2 plus 1, which is a sub 3 equals 1/2 times a sub 2 plus 6. And again, you see to get a3, you had to know a2. So we had to have done this calculation in order to do this one. A2 was 5, so this is 1/2 times 5 plus 6. And now we're no longer an integer. This is 11/2, which is 5.5. If you plug n equals 3 into the recurrence relation, you get a4 equals 1/2 times a3 plus 6, which is 1/2 times 11/2 plus 6, which is, so 6 as a ratio over 2 is 12/2. 12/2 plus 11/2 is 23/2 times 1/2 is 23/4. 20 over 4 is 5. So this is 20 over 4 plus 3 over 4, which is 5.75. And I will do just one more. If you plug in n equals 4 to the recurrence relation, you get a5 equals 1/2 times a4 plus 6. A4 we just found is 23/4. So this is 1/2 times 23/4 plus 6. 6 as a ratio over 4 is 24/4 plus 23/4 is 47/4 times 1/2 is 47 over 8. And 1/8 is 0.875, right? So 7/8 is 0.875. So this is going to be 5.875. So looking at the first, I guess, 6 terms here, if you count the n equals 0 term, looking at the first few terms here, 2, 4, 5, 5.5, 5.75, 5.875. Does anybody have a guess for this limit? Yeah, it appears to be the case that this sequence is converging to the number 6, right? It appears to me that these terms are getting closer and closer and closer to 6. And there's kind of 2 separate statements we could make there. It appears that n to infinity of an 6 the sequence AN converges to 6. Remember what it means for a sequence to converge. It means that the sequence has a finite limit. And from the work we've done here, just writing out the first few terms, that seems like it might be the case. Is this a guarantee that that's true? No, not at all, right? Looking at the first few terms, the sequence could do some crazy ass shit, like maybe A6 is 12, maybe A7 is -10. But from what we've done so far, it at least appears that way. And we could compute more terms. We could compute A6, A7, A8, A9, and this is correct. This is a true statement. To prove that this is a true statement is a different matter. And in this class, it is like just barely too much of a stretch because it requires something called mathematical induction. And so I'm not going to put you guys through that. The honors class, I require them to give inductive proofs for this sort of thing. But I do want to talk about the theorem that's generally used. And I also want to talk about the sort of standard trick for recursive sequences. Yeah, that's correct. So as long as the terms get closer and closer and closer to 6 and stay close to 6, right? Continually get closer and closer to 6, then we would say that the limit is 6, i.e. the sequence converges to 6. The problem is that just from listing a few terms, I can't guarantee that it doesn't start doing something weird later on, right? Maybe the terms get closer and closer to 6 for the first 10,000 terms, but then after that, for whatever reason, maybe the terms start getting closer to 12 or, blowing up to infinity. So we would say this is evidence in favor of the limit being 6, but it is far from a proof. The trick to finding the limit of a recursive sequence and just to be clear, right? So we always want to know what we're going to be tested on. When it comes to exams, I could and very well might ask you to list the first few terms of a recursive sequence, and I might ask you to guess at the limit or tell me whether you think the sequence converges or diverges. I would not require you to employ the following theorems or techniques, although I do want to show them. Trick to finding the limit of a recursive sequence is to take lim n to infinity everywhere in the recurrence relation with the assumption that lim n to infinity an exists, and we give it a name. We call it L. There's one other little bit of information or thinking that is required here, and I'll address that as we do it here. So for the problem above, this yields lim n to infinity an plus 1 would be on the left, and on the right I would have lim n to infinity 1/2 an plus 6. And you can use all your limit laws, right? All your limit laws from Calc 1 are totally kosher here, namely the 1/2 can pop out. The limit of the constant 6 would be 6. The tricky biscuit is this guy. Let me say over here. if when n to infinity an equals L, what can you say about the limit as n goes to infinity of a sub n plus 1? Or what is the relationship between an plus 1 and an? We saw this on Wednesday a little bit when we talked about geometric sequences. What does an plus 1 even mean? Don't be shy. If I'm talking about a sequence where an is the nth term of the sequence, what is an plus 1? Forget about the limit for a minute. Just, if an is the nth term, then an plus 1 is the it's connected to an. It's the term that comes after an, right? It's the n plus first term. It's like if n is 5, then an is a5, and an plus 1 is a6. An plus 1, this thing here, forget about the limit for a minute, this thing is the term that comes after an, right? And that's what the recurrence relation is. It tells you how to get the next term from the previous term. So what would be the limit as n goes to infinity of this thing related to the limit as n goes to infinity of this thing? Would they be the same or different? Okay. So if we're saying that the limit as n goes to infinity of an is this number L, that's like saying a sub infinity is L, right? We're like plugging in infinity. That's sort of the thing that we're trying to do here. The trick is, of course, that infinity is not a number. It's a weird thing. But if you're okay with saying that lim n to infinity of an is the same thing as plugging in infinity, then the limit as n goes to infinity of a sub n plus 1 as n goes to infinity, n plus 1 also goes to infinity. This would also be a sub infinity. So that would also be L. That's the idea here. If the nth term of a sequence goes to L, then the n plus first term of that sequence goes to L. It's literally just the next term. Or if you're thinking about the graph, right? If you're thinking about the dots, an is the nth dot. And we're saying as n gets bigger and bigger and bigger, the nth dot gets closer and closer to L. An plus 1 is the n plus first dot. It's the one that comes after an. So if an is getting closer and closer to L as n gets bigger and bigger, an plus 1 must also be getting closer and closer to L. So if lim n to infinity of an is L, then lim n to infinity an plus 1 is also L, which means that the expression above can be read as L equals 1/2 times L plus 6. This piece goes to L, and this piece goes to L. The 1/2 and the 6, they're constants. They don't change with n. And this is an equation that we can very easily solve for L. It's a linear equation. Multiply both sides by 2. Subtract L from both sides. So if you're allowed to assume that the limit of the an exists, then that limit must be 6 from the recurrence relation. Pretty cool, right? So we thought that that limit was 6. We wrote down the first few terms. We're like, oh yeah, it's getting closer and closer to 6. If you take limits everywhere in the recurrence relation as n goes to infinity, and assume that the sequence is a convergent sequence, i.e. that that limit exists, give it a name, call it L, then you will end up with an equation that you can solve for L, which is a very neat trick. The challenging thing here is, how do we know that the limit exists? And that is very much an existential question, right? By definition of the word existential. And the easiest way to resolve it is with a theorem. And I will share with you that theorem, but the actual application of the theorem requires work with mathematical induction most of the time. So I'm not going to ask you to employ the theorem, but the theorem is this. I'd be a bad calc teacher if I didn't show you this. Is that bounded monotone sequences converge? I think it's a fun theorem because it's like there's no math symbols in it anywhere. It's just a few words. But of course, there are math symbols buried in the words. So what does bounded mean? What does monotone mean? The word bounded in the context of a sequence, if you think about what the word bounded means in English, it means that there is a boundary, a thing you can't get out of. And for a sequence, what this means is that for some number, some fixed constant m, the inequality absolute value of an is less than or equal to m is true for all numbers n. That's what the word bounded means for a sequence. And I'll show you this in terms of the graph. But it just means that the terms of the sequence can't run away to infinity, right? That's what this means. It means that there is a maximal size to the terms of the sequence, right? Can't possibly be bigger than m. So kind of find the largest term of the sequence. That's an upper bound for the sequence. Monotone this is actually saying two things at once. This means either always increasing or always decreasing. leave some space, because I'm going to give you two ways to characterize each of these. So increasing and decreasing certainly are terms that you know from Calc 1, even before, right? Your algebra classes talked about increasing and decreasing functions. If I'm talking about a sequence, then there is a kind of convenient way to write this. Always increasing means a sub n plus 1 is always greater than or equal to a sub n. That would be for all n. Always decreasing means a sub n plus 1 is less than or equal to an for all n. And again, the trick is to remember that a sub n plus 1, and you're going to have to get comfortable with this because this is going to show up again and again and again. A sub n plus 1 is just the next term. If an is a term of the sequence, an plus 1 is the next term of the sequence. So what this inequality says is that the next term is always bigger than the term that came before. Right? This is actually much harder to define for functions, right? Functions of a continuous variable like you've dealt with in the past, because there is no next real number. So we had to do it in terms of like slopes or you know, shit like that, thinking about the shape of the graph, or some inequality with, quite frankly, complicated quantifiers underlying it. And the statement here, next to always decreasing, an plus 1 is less than or equal to an, says that the next term is always smaller than the term that came before. Well, okay, yeah, if the next term is always smaller than the term that came before, that means you're always going down. And if the next term is always bigger than the term that came before, that means you're always going up. So these make intuitive sense. We've mentioned that taking derivatives of sequences, well, you can't really think about it in terms of tangent lines or anything like that, can be done by thinking about a corresponding function. And as you know from Calc 1, these statements, you know, this function is increasing or this function is decreasing, can be parsed in terms of the sign of the derivative. So I'm going to add here a kind of second way of thinking about this. Increasing could mean that the derivative of an, if you take an and you prime it, where prime is derivative taken with respect to n, is positive, or at least non-negative. And here, the derivative would be non-positive, or less than or equal to 0. Right, and what's going on there when I think about derivatives, I'm really thinking about the related function that matches with my sequence on the integers and then differentiating that function. But just like with L'Hopital's rule, where we say, okay, it's just symbol shuffling. We can just differentiate the original thing using our differentiation rules and get the same result. That's what we're saying here. So these are what the terms bounded and monotone mean. And the theorem says that if a sequence is both bounded and monotone, it must be convergent. I'd like to convince you that this is true, but I also don't want to spend too much time on it because it's a beautiful, deeply theoretical thing that you won't be using very much at all. So let's do it, but just with pictures. It's proof without words. Why are bounded monotone sequences convergent? Well, we have to think about a bounded increasing sequence and a bounded decreasing sequence separately. So suppose AN is bounded and monotone increasing. The inequality absolute value of AN is less than M. Equal to M means the way you unpack these inequalities. Yes, yeah, the word here is proof. The way you work with an inequality like this, like the absolute value of some stuff is less than some number, is by writing it as the negative of that number is less than or equal to that stuff is less than or equal to the positive version of that number. This rule right here is true for all sorts of absolute value inequalities, any absolute value inequality of this form. So let's try to draw the graph of such a sequence. Here's my n axis, and this is the graph y equals an. Let's say m is here, which means negative m would be down here. And I've said that this sequence is bounded by m, which means that on the one hand, an is always less than or equal to m, can't go above that line. On the other hand, an is bounded below by negative m, can't go below this line. So the terms of the sequence are trapped in this window. They can't escape. That's what bounded means. The other thing that we're assuming here is that this is a monotone increasing sequence. So, okay, let me just start trying to draw the graph of an arbitrary monotone increasing sequence that is trapped in this window, and see if you can't start understanding why such sequences must converge. Maybe A0 is like down here or something. Can't be below this because I'm not allowed to go through that floor because I'm bounded. Maybe A1 is like up here. Maybe A2 is up here. I have to go up each time. I'm not allowed to go down, right? Because I'm increasing. So the next one has to go up. The next one has to go up. It always has to go up. But I'm also not allowed to go through this ceiling. Oh shit. Oh shit. We're stuck. Well, what does this look like? The next term has to go up, but can't go through that ceiling. All these dots are going to start piling on to this upper bound. We're not allowed to turn and go down because we're increasing. Always have to go up. But I'm not allowed to go through that upper bound. I'm stuck. So all those terms have to start piling up on that ceiling. And that means that this sequence has a limit, right? Namely, m. So, all these terms, they've got no choice but to get closer and closer and closer to m. That must be a convergent sequence. It has no choice. And if the sequence were decreasing, the same thing would happen, but with the floor. The terms would all pile up on the floor. Can't poke down through the floor, but can't turn around and go back up. So if you have a bounded monotone sequence, that sequence is automatically convergent. And I'll just tell you that with recursive sequences, when we get to that place where like, okay, I want to find the limit, we take the limit as n goes to infinity everywhere in the recurrence relation, and we had to assume when we did this a moment ago, that the limit exists. The way you would prove that the limit exists is by proving that that sequence is bounded and monotone. That requires the use of induction. That's not something that can be done easily, at least in most cases. And so it's not something I will require you to do. But I do want you to understand that this is the machinery that's going on underneath that process. And this terminology is terminology you should be familiar with. What does it mean for a sequence to be bounded and monotone? And when you are asked about bounded and monotone sequences, the picture you should have in your head is this one. Right? The terms of the sequence piling up on the ceiling, but not being able to break through, also not being able to go back down. So they have no choice but to go to that limit. It's actually, I think, quite beautiful. Okay. This is the proof. Again, you're not responsible for the proof, but I want you to be aware of it. What you are responsible for is being able to list the first few terms of a recursive sequence and guess at whether the sequence is or is not convergent. Right? Guess at the limit. So let's look at some other recursive sequences. A famous recursive sequence, which I will suggestively name Fn, is defined by the recurrence relation F sub n equals F sub n minus 1 plus F sub n minus 2, and the initial conditions that F sub 0 is equal to 0 and F sub 1 is equal to 1. I'd like to list the first, again, we'll just say 5 terms. And we could also say, and yes, at the limit as n goes to infinity of F sub n. Okay. They gave us F0 and F1. So the next term would be F2. And this recurrence relation has Fn on this side. So if I want F2, I can just plug 2 in for n everywhere here. The left-hand side, I get F2. Over here, I get equals F sub 2 minus 1. Well, that's F sub 1. Plus F sub 2 minus 2. That's F0. F0 I was told is 0. F1 I was told is 1. So this is 1 plus 0, which is also 1. Plugging n equals 3 into that recurrence relation, I get F3 equals F2 plus F1. F2 I just calculated is 1, and F1 was given to me. That's also 1, so this is 1 plus 1, which is 2. Very exciting, I know. If I plug n equals 4 into that recurrence relation, it says F4 is equal to F3 plus F2. F3 I just calculated is 2, F2 is 1. So this is 2 plus 1, which is 3. Let's go a few more. F5 would be F4 plus F3. That is 3 plus 2, which is 5. F6 would be F5 plus F4, which is 5 plus 3, which is 8. And I'll stop at the next one. F7 would be F6 plus F5, which would be 8 plus 5, which is 13. Anybody recognize this sequence? 0, 1, 1, 2, 3, 5, 8, 13. It is quite famous. Around the time I was an undergrad, there was a very popular book by an author named Dan Brown called The Da Vinci Code. And for a few years, everybody knew what this sequence was. I'm kind of glad to see that it's not the case anymore because that book is not great. This is the Fibonacci sequence. And a lot of kind of mathematicians, people who are loosely interested in mathematics, get very excited about the Fibonacci sequence because there are ways to connect it to this thing called the golden ratio. If you divide two consecutive terms here, kind of like you're looking for the common ratio of a geometric sequence, if you pretend that this is a geometric sequence and divide two consecutive terms, you don't get a constant, right? 13 over 8 or 8 over 5 or 5 over 3, those are not the same number. But they do get closer and closer to a special number called the golden ratio. Finding an explicit formula for the nth Fibonacci number is quite tricky. It can be done, but it involves some very complicated work with generating functions or things called forward difference equations. But that's all. We were just trying to list the first few terms. We've succeeded at that. This thing is called the Fibonacci sequence. Does anybody have, yeah, exactly, a guess at the limit? Just looking at these guys. So of course the rule is, what this says is to get the next number, just add the two previous ones. So the next one would be 13 plus 8. So definitely an increasing sequence. Do we think it's bounded? Yeah, no. And any unbounded sequence is automatically divergent. So it's true here that the limit as n goes to infinity of fn is definitely positive infinity. This thing just grows and grows and grows and grows. So that's not really a guess. We could show that quite conclusively, but just looking at the first few terms, you can deduce that this guy is definitely going to infinity, right? The next term would be 21, and then after that would be 32, and then after that it just keeps going. A fun fact. If you take the limit as n goes to infinity of the ratio of two consecutive terms, this is what I was saying a second ago, This gives you that golden ratio, sometimes called phi. 1 plus the square root of 5 over 2. But the sequence itself diverges. Okay, that's enough time on the Fibonacci sequence. Well, maybe one more thing. The explicit formula for the Fibonacci sequence involves this number. In fact, powers of this number. Yeah, that's all. There are two other recursive sequences I want to play with here. And then if there's time after that, we can just play around with some example problems where we practice taking limits, because that's a skill we really do need to practice. The next example I'm going to play with is AN be the sequence defined by AN plus 1 is equal to the square root of 3 times AN, and say A0 is equal to 1. Yeah, sure. Same thing, list the first few terms. And guess that the limit as n goes to infinity of AN. This is sort of a strange recurrence relation. The next term is the square root of 3 times the previous term. So if I get in here and start listing terms, I was told that A0 is 1, so that starting term there is 1. A1 would, according to my recurrence relation, be the square root of 3 times A0. And A0 is 1, so this is the square root of 3 times 1, or just the square root of 3. A2 would be the square root of 3 times A1, which is the square root of 3 times the square root of 3, nested like this. A3 would be the square root of 3 times A2, which is the square root of 3 times A2. A2 is the square root of 3 times the square root of 3. So you've got these nested square roots of 3. We'll go a few more, but hopefully you see what this is doing. It's again, quite strange, but I'm sure we will see the pattern. A4 is the square root of 3 times A3. That means I'm going to have this big square root outside, and then a 3, and then this whole thing inside. So that's the square root of 3 times this whole thing. And maybe I'll stop here. We've got A0, A1, A2, A3, and A4. That would be the first 5 terms. Yeah, definitely a strange sequence, but we're just following this recurrence relation. So if you plug n equals 0 into this recurrence relation, you get that a1 is equal to the square root of 3 times a0. So that's this, a1 is equal to the square root of 3 times a0, and a0 was 1. Yeah, so every time n goes up by 1, we're like putting another 3 out front and taking the square root of the whole thing. Definitely strange. Definitely strange. Now, just for fun, we said we wanted to guess at the limit. This is a case where I can actually show you what the limit is conclusively. But we'll look at a few terms here. And then I have a funny story around this one. When I first moved to Gainesville, I was very into math. Wanted to meet people, but a little bit awkward. So on the parking lot out in front of my apartment, I wrote out an infinite nest of square roots, right? Like I wrote something like this, but with a dot, 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 indicating that it goes on and on forever, and then equals, and then the answer. And I left it there. And after about a week went by, someone knocked on my door to argue with me about the claim, which was fun. And we sat down, and I don't think he ever believed me, but they did become a friend. Let's see if we can do better. So, square root of 3, about 1.7. 1.73. What about the square root of 3 times the square root of 3? That's a2. That's 2.28-ish. And if I take the square root of 3 times the square root of 3 times the square root of 3, that's a 3. 2.62-ish. And then this last guy would be the square root of 3 times the square root of 3 times the square root of 2.8-ish. And it's not immediately obvious what's going to be the limit, is it? It does appear that this is an increasing sequence. Right? These terms are all getting bigger and bigger. And it's actually pretty easy to show that this one is increasing. Because multiplying by root 3 and multiplying by 3 always makes you bigger, right? And if you take the square root of a bigger thing, that's going to be bigger. So an plus 1 will always be bigger than an. But what's not immediately clear is that it's bounded. And again, a proof there would require some induction, so we're not going to go through it. But it is true. It is true. Turns out that this sequence is monotone increasing and bounded. So the limit as n goes to infinity of an exists, and I can call it L. must exist. And then if I take this recurrence relation and send n to infinity everywhere in that, this must exist and must satisfy when n to infinity an plus 1 equals when n to infinity square root of 3an. And we said earlier that, if an has limit L, then an plus 1 has to have limit L. So this would say L is equal to the square root of 3L. And that's an equation we can solve. Square both sides. You get L squared equals 3L. So subtract 3L from both sides. You get L squared minus 3L equals 0. Factor in L. You get L times L minus 3 equals 0. So either L equals 0 or L equals 3. This is an increasing sequence, and the first term is 1. So the limit can't be 0 because we can never go down. Since the sequence an is increasing, and a0 equals 1, it's not possible for L to be 0. So L equals 3 must be correct. In other words, this sequence converges to 3. And that's true. If you take an infinite nest of square roots, that's really what we're saying. The square root of 3 times, 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 infinitely nesting those square roots down. That's 3. This was the claim that the fellow knocked on my door to dispute. I think I did it with 7s or something, but yeah, it's true. It really is true. And there's nothing magic going on. It's just a matter of understanding the definitions and how the mechanics of these things work. It absolutely works. Such a sequence must have a limit satisfying this equation. This equation has 2 solutions, 0 and 3. 0 is impossible because the sequence is always going up and it starts at 1, so it can't turn around and go down to 0. The only possibility then is that it's getting closer and closer to 3. And that is the correct statement. So yeah, this is a cute example. I always get excited in the day we get to talk about this one because it's so much fun, and it's connected to a fun story and time in my life where I got to do some mathematics with a complete stranger who was very adamant that this was not true, but it is true. So other important recursive sequences, there's one major important recursive sequence that we need to talk about, and that's called the factorial sequence. It's not as much fun in the sort of playful way as this is, but it is way more important down the road. So let's do it. I'm not going to beat around the bush here. I'm going to show you the notation right away. It's a little bit weird. The factorial. The definition, so instead of, I'll just show you. The factorial of n written n exclamation mark. The recurrence relation is that n plus 1 exclamation mark or n plus 1 factorial is defined to be n plus 1 times n factorial. This is your recurrence relation. And the initial condition or initial value is that 0 factorial is the number 1. And this bothers people, but don't be bothered by it. It's just a definition. It can be justified combinatorially, lots of different ways. Let's list the first few factorials. Let's see, 1 factorial, if I plug in n equals 0 here, should be 0 plus 1 times 0 factorial. 0 plus 1 is 1. 0 factorial is 1, and 1 times 1 is 1. So I'm plugging n equals 0 into this expression, and then using this initial condition. 2 factorial. So now I'm plugging n equals 1 in here, right? 1 plus 1, 2 factorial. 2 factorial is 1 plus 1 times 1 factorial, which is 2 times 1. And of course, that is 2. Continuing, 3 factorial. So I'm plugging n equals 2 in here. Is 2 plus 1 times 2 factorial, which is 3 times, and then 2 factorial was 2 times 1. 3 times 2 times 1, that's 6. 4 factorial. So now I'm plugging n equals 3 in here. Would be 3 plus 1 times 3 factorial. 3 plus 1 is 4. So this is 4 times 3 factorial, which is 3 times 2 times 1. Which is 4 times 6, or 24. 5 factorial is 4 plus 1 times 4 factorial, which is 5 times 4 times 3 times 2 times 1, which is 120. I'll stop here for now. The reason I'm writing the kind of second to last column the way I am is to illustrate the closest thing to a nice formula for the factorial that we can get. Look at 5 factorial. It's 5 times 4 times 3 times 2 times 1. What do you think 6 factorial is? That would be 6 times 5 times 4 times 3 times 2 times 1. Right? 10 factorial. Let's look at the patterns in here. It would be 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. So n factorial is n times n minus 1 times n minus 2 times, and you go all the way down to 3 times 2 times 1. And this works great as long as n is bigger than 1. If n is 0, again, remember 0 is defined to be 0. 0 factorial is defined to be 1. this is what you should this is what you should hold on to for your definition of the exclamation mark symbol. And these things are going to show up everywhere. The reason they show up everywhere is because if you take the derivative of a power function until the thing becomes constant, like if you differentiate x to the 5 over and over and over again, first derivative is 5x to the 4. Second derivative is 5 times 4, x to the 3. The next derivative is 5 times 4 times 3 times x to the 2. If you keep differentiating until the x goes away, you get 5 times 4 times 3 times 2 times 1, which is 5 factorial. So the fifth derivative of x to the 5 is 5 factorial. The nth derivative of x to the n is n factorial. That's one reason why these are super duper important. Another reason is combinatorial. Yeah, the word is factorial, like factor, but with an EL at the end, factorial. You can kind of think of it like it's a bunch of factors multiplying each other, right? One of your homework problems this week, and this will be the last thing I do here today. One of your homework problems this week has you simplifying a ratio of factorials. And the factorial as an operator, as a function, is kind of fucking weird. Like, so often we want to do algebra things that aren't quite kosher, right? Like distributing square roots. That's one I see all the time, saying the square root of x squared plus 1 is x plus 1, distributing square roots. There are things like that that people want to do with factorials that aren't kosher. And then there are things that we need to learn how to do, right? What is the kosher way to handle stuff like that? So let's look at some examples of problems involving factorials that are related to limits of sequences. That's correct. Yeah, so the next one would, if 2 factorial is that, the next one would be 3 times 2 times 1. Exactly. So one of your homework problems has you taking a limit of something like this, right? If you look through your homework for this week, one of them is like something factorial over something else factorial like this. And you're told to take the limit as n goes to infinity. Well, let's see if we can simplify this and put it into a form where we could even hope to take the limit. The trick is in understanding what the fuck 2n plus 1 factorial even means. And I'll tell you at the start, it's not 2 times n factorial plus 1. You can't distribute the factorial. That doesn't work. It's also not a multiplicative function. It's not the whole fraction with 1 factorial. That also doesn't work. There's, in fact, very little you can do algebraically with the factorial. Besides, write it out. So I'd say recall, like, well, let's look at the first few terms here. So A1 would be 2 times 1, which is 2, minus 1, that's 1 factorial. And downstairs here you'd have 2 times 1 plus 1, that's 3 factorial. 1 factorial is 1. 3 factorial is 3 times 2 times 1. So this would be 1/6. A2 would be 2 times 2 minus 1, which is 4 minus 1. That's 3 factorial divided by 2 times 2 plus 1. That's 5 factorial. So the top here is 3 times 2 times 1. And the bottom here is 5 times 4 times 3 times 2 times 1. And what you see is that 3 times 2 times 1, 3 times 2 times 1, this cancels. This is 1 over 5 times 4, or 1 over 20. A3 would be 6 minus 1, which is 5 factorial upstairs, and 6 plus 1, which is 7 factorial downstairs. So the top is 5 times 4 times 3 times 2 times 1. And the bottom is 7 times 6 times 5 times 4 times 3 times 2 times 1. And what you notice is that, again, the whole top cancels. 5 times 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. And you're just left with 2 terms on the bottom. 1 upstairs, 1 over 7 times 6, which would be 1 over 42. So looking at the first few terms here, 1/6, 1/20th, 1/42nd, those are getting small. And we might guess that the limit here is 0, and this would be an acceptable way to solve that homework problem. But I didn't ask for the limit here. I asked you to simplify this, meaning I want you to write it without any factorials. I don't want 1 of the terms or 5 of the terms or the limit. I want a new expression for this that is free of exclamation points. How do you do that? Well, you want to do this thing, but instead of doing it when n is equal to 3, you want to do it in general when n is just n. And that requires writing out 2n minus 1 factorial and 2n plus 1 factorial. So what's going on? When you take the factorial of something, like the factorial of 3, starts with that thing, and then multiply by the number right below it, multiply by the number right below that, multiply by all the numbers less than or equal to the thing until you get down to 1. So upstairs, 2n minus 1 factorial would start with 2n minus 1, just like 3 factorial starts with 3 and 5 factorial starts with 5. The next number in this product is like start with 5. Okay, the next one will be 4. Well, if I'm starting at 2n minus 1, what's the next number immediately below that? How do you go from 3 to 2, or from 5 to 4, or from 7 to 6? Yeah, you subtract 1, right? So the next term in the numerator, if I'm starting at 2n minus 1, is going to be the number right below that, or that number minus 1. 2n minus 1 minus 1 is 2n minus 2. So that's like the 5 times 4. The next number right below 2n minus 2 is 2n minus 3. The next one would be 2n minus 4, then 2n minus 5. Where'd it come from? Not sure I see a 1/3 anywhere. One factorial over 3 factorial. Yeah, so I plugged in 1 for n here. All right, that's a1. So this comes from just taking n equal to 1 here, n equal to 2 here, n equal to 3 here. I'm listing the first few terms. So let's finish what we're doing here, and then we can pause for questions. So 2n minus 1 factorial, just like 5 factorial is 5 times 4 times 3 times 2 times 1, is going to be 2n minus 1 multiplied with all the numbers less than or equal to that until you get down to 1. And normally the way we write this is like by ending the product with 3 times 2 times 1. The downstairs of this fraction is 2n plus 1 factorial. So that's like here, 7 factorial. It's going to start with 2n plus 1, just like 7 factorial starts with 7 and 5 factorial starts with 5. This is going to be 2n plus 1. And then what I need to do is multiply this by all the numbers less than or equal to it. So just like to go from 7 to 6, you subtract 1. To go to 5, 4, you subtract 1. To go from the start of this factorial to the next term in the product, you would subtract 1. That's going to give you 2n, right? 2n plus 1 minus 1 is 2n. And then the next term in that downstairs, subtract 1. So that's 2n minus 1. Next term, subtract 1, that's 2n minus 2. Subtract 1, that's 2n minus 3. All the way down till you get to 1. So if, look at A2, right? In A2, all the terms from the top canceled. And what was left over was just the first 2 terms from the factorial in the denominator, 5 times 4. In A3, all the terms from the top canceled, and what was left was just the first 2 terms from the denominator, 7 times 6. A4 would be 7 factorial over 9 factorial, and you might deduce from this pattern that all you would have after you cancel everything is 1 over 9 times 8, and that's correct. If you look here, this whole thing cancels with this whole thing. And all that's left are the first 2 terms of the factorial from the denominator. Two n plus 1 times 2n. Canceling factorials is an art form, and you need to practice it. There are other problems in the textbook. I only assigned the 1 because I don't want to overwhelm you. But it is a delicate thing that requires some practice. Now, unfortunately, we don't have more time to play with these today, but if you use this as a model, then you will be able to get to where you need to get. So I'm just writing out each one. So 1 factorial is 1, and 3 factorial is 3 times 2 times 1. So just the top is equal to the top, the bottom is equal to the bottom. Not doing anything crazy there, just writing down the definition of each of those things. And that's the same thing that we're doing in each of these lines here. It's just to kind of help us see the pattern so that when we do this, it's not super surprising. That was really my intent there. I'm sorry if it only served to confuse. Well, while you guys digest this a little bit, I'm going to make a suggestion. Is n squared factorial the same as n factorial squared? Is 2n factorial the same as 2 times n factorial? What other fun stuff could we do? Is n plus m factorial the same as n factorial plus n factorial? Lots of questions like these exist. The answer to most of them is no, but the fun path is to write out both objects and see if you can understand why they're different. So the answer to each of these questions is no. but I invite you to explore why. We will have to wrestle with things like this, not infrequently, especially towards the end of chapter 11. So we're introducing them now, try and get you used to them. It's a fun notation. If you go on to invent more mathematics, please don't use punctuation marks for operators though, because holy shit, is that like confusing. Okay, I'm gonna go ahead and end the meeting here. If you want to talk more about this or any other stuff, of course, you can come see me in office hours. Work hard on that sequences homework. This is the basis for everything we're going to be doing throughout the rest of chapter 11. Chapter 11 is a long chapter. It's got, I think, 10 or 11 sections that we're going to cover in detail. So please work hard on this stuff. Everything we do in chapter 11 will be built upon what we're doing right now in 11.1. That's why I stretch it out to a whole week. Next week, I'm going to introduce infinite series, and we are going to move quite quickly through section 11.2 and 11.3, which are kind of the definition of infinite series and some basic series to work with, and then something called the integral test, where you relate an infinite series back to a type 1 improper integral. But all of that is for next week. For now, worry about sequences. Reach out to me if you need help with anything, and I'll see you guys on Monday.